Hello and welcome to the session on K-means clustering. I'm Douglas from Simplilearn. So what is K-means clustering? K-means clustering is an unsupervised learning algorithm. In this case, you don't have labeled data, unlike in supervised learning. So you have a set of data and you want to group them, and as the name suggests, you want to put them into clusters, which means objects that are similar in nature. Similar in characteristics. They need to be put together. So that's what K-means clustering is all about. The term K is basically a number, so you need to tell the system how many clusters you need to perform. So if K is equal to 2, there will be 2 clusters. If K is equal to 3, 3 clusters, and so on and so forth. That's what the K stands for. And of course, there's a way of finding out what is the best or optimum value of K for given data, and we will look at that. So that is K-means clustering. So let's take an example. K-means clustering is used in many scenarios, but let's take an example of cricket, the game of cricket. Let's say you received data of a lot of players from maybe all over the country or all over the world. And this data has information about the runs scored by the people, ordered by the player, and the wickets taken by the player. And based on this information, we need to cluster this data into 2 clusters, batsmen and bowlers. So this is an interesting example. Let's see how we can perform this. So we have the data which consists of primarily 2 characteristics, which is the runs and the wickets. So the bowlers basically take the chips and the batsmen score the runs, and there will be, of course, a few bowlers who can score some runs. And similarly, there will be some batsmen who would have taken a few wickets. But with this information, we want to cluster those players into batsmen and bowlers. So how does this work? Let's say this is how the data is. So there are information. There is information on the y-axis about the runs scored, and on the x-axis about the wickets taken by the players. So if we do a quick plot, this is how it would look, and then we do the clustering. We need to have the clusters like shown in the third diagram out here. We need to have a cluster which consists of people who have scored high runs, which is basically the batsmen. And then we need a cluster with people who are taking a lot of wickets, which is typically the bowlers. Now, there may be a certain amount of overlap, but we're not going to talk about that right now. So with K-means clustering, we see here that K is equal to 2, and we will have 2 clusters, which is the batsmen and the bowlers. So the way this works is the first step in K-means clustering is the allocation of 2 centroids randomly. So 2 points are assigned and as so-called centroids. So in this case, we want 2 clusters, which means K is equal to 2. So 2 points that have been randomly assigned as centroids. So keep in mind these points can be anywhere. They're random points, and they're not, initially anyway, they're not really the centroid. Centroid means it's a central point of a given data set. But in this case, when it starts off, it's not really the centroid. Okay, so these points, so in our presentation here, we have shown them at 1 point closer to these data points and another closer to these data points. They can be assigned randomly anywhere, okay? So that's the first step. The next step is to determine the distance of each of the data points from each of the randomly assigned centroids. So for example, we take this point and find the distance from this centroid and the distance from this centroid. This point is taken, and the distance is found from this centroid and this, and so on and so forth. So every point, the distance is measured from both the centroids. And then whichever distance is less, that point is assigned to that centroid. So for example, in this case, visually it is obvious that all these data points are assigned to this centroid, and all these data points are assigned to this centroid. And that's what is represented here in the blue color and in this yellow color. The next step is to actually determine the central point or the actual centroid for these 2 clusters. So we have this one initial cluster, this one initial cluster. But as you can see, these points are not really the centroid. Centroids means it should be the central position of this data set. Central position of this data set. So that is what needs to be determined as the next step. So the central point on the actual centroid is determined, and the original randomly allocated centroid is repositioned to the actual centroid of this new cluster. And this process is actually repeated. Now what might happen is some of these points may get reallocated. In our example, that's not happening, probably. But it may so happen that the distance is found between each of these data points, once again with these centroids. And if it is required, some points may be reallocated. We'll see that in a later example. But for now, we'll keep it simple. So this process is continued until the centroid repositioning stops. And that is our final cluster. So this is our final iteration. We've come to this position in this situation where the centroid doesn't need any more repositioning. And that means our algorithm has converged. A convergence has occurred, and we have the cluster, or two clusters. We have the clusters with a centroid. So this process is repeated, and the process of calculating the distance and repositioning the centroid is repeated until the repositioning stops, which means that the algorithm has converged. We have the final cluster with the data points and the centroids. So this is what you're going to learn from this session. We'll talk about the types of clustering, what is k-means clustering, application of k-means clustering. K-means clustering is done using distance measure, so we will talk about the common distance measures, and then we will talk about how k-means clustering works and go into the details of the k-means clustering algorithm. And then we will end with the demo and a use case for k-means clustering. So let's begin. First of all, what are the types of clustering? There are two primary categories of clustering, hierarchical clustering and then partitioning clustering. And each of these categories are further subdivided into agglomerative and divisive clustering, and k-means and fuzzy c-means clustering. So let's take a quick look at each of these types of clustering. In hierarchical clustering, the clusters have a tree-like structure, and hierarchical clustering is further divided into agglomerative and divisive. Agglomerative clustering is a bottom-up approach. We begin with each element as a separate cluster and merge them into successfully larger clusters. So, for example, we have A, B, C, D, and F. So we start by combining B and C in one cluster, D and E form one more, and then we combine D, E, and F, a larger cluster, and then B and C, and then finally add A. So we'll compare that to divisive clustering. So divisive clustering is a top-down approach where we begin with the whole data set and proceed to divide it into successfully smaller clusters. So we have A, B, C, D, E, F. We first take that as a single cluster and then break it down into A, B, C, D, E, and F. Then we have partitioning clustering, split into two subtypes, k-means clustering and fuzzy c-means. In k-means clustering, the objects are divided into the number of clusters mentioned by the number k. That's where the k comes from. So if we say k is equal to 2, the objects are divided into two clusters, C1 and C2. And the way it is done is the features or characteristics are compared, and all objects having similar characteristics are clubbed together. So that's how k-means clustering is done. And we'll see that more in detail as we move forward. Now, fuzzy c-means is very similar to k-means in the sense that it clubs objects that have similar characteristics together. But while in k-means clustering, two objects cannot belong to, or any object, a single object cannot belong to two different clusters, in c-means, objects can belong to more than one cluster. So that's the primary difference between k-means and fuzzy c-means. So what are some of the applications of k-means clustering? K-means clustering has a variety of uses or a variety of business cases in real life, starting from academic performance, diagnostic systems, search engines, and wireless sensor networks, and many more. So let's take a deeper look at each of these examples. Academic performance. So based on the scores of students, students are categorized into A, B, C, and so on. Now, clustering forms a backbone of search engines. When a search is performed, the search results need to be grouped together. Then the search engines very often use clustering to do this. And similarly, in the case of wireless sensor networks, the clustering algorithm plays the role of finding the cluster heads, which collects all the data in its respective cluster. So clustering, specifically k-means clustering, uses distance measure. So let's take a look at what distance measure is. So while these are different types of clustering, in this video we will focus on k-means clustering. So distance measure tells how similar some objects are. So the similarity is measured using what is known as distance measure. And so what are the various types of distance measures? There is Euclidean distance, there is Manhattan distance, then we have squared Euclidean distance and cosine distance measure. These are some of the distance measures supported by k-means clustering. Let's take a look at each of these. So what is Euclidean distance measure? This is nothing but the distance between 2 points. As we learned in high school how to find the distance between 2 points. So this is a sophisticated formula for that. But we know a simpler one is the square root of y2 minus y1 whole square plus x2 minus x1 whole square. So this is just an extension of this formula. And that's the Euclidean distance between 2 points. What is the squared Euclidean distance measure? It's nothing but the square of the Euclidean distance, as the name suggests. So instead of taking the square root, we leave the square as it is. And then we have Manhattan distance measure. In the case of Manhattan distance, it is the sum of the distances across the x-axis and the y-axis. And note that we are taking the absolute value so that the negative values don't come into play. So that's the Manhattan distance measure. Then we have cosine distance measure. In this case, we take the angle between the two vectors formed by joining the points from the origin. So that's the cosine distance measure. Okay, so that was a quick overview about the various distance measures that are supported by k-means. Now, let's check how exactly k-means clustering works. Okay, so this is how k-means clustering works. This is like a flow chart of the whole process. There's a starting point, then we specify the number of clusters that we want. Now there are a couple of ways of doing this that we can do by trial and error. So we specify a certain number, maybe k is equal to 3 or 4 or 5 to start with, and then as we progress we keep changing it until we get the best clusters. Or there's another technique called the elbow technique, whereby we can determine the value of k, or what should be the best value of k, and how many clusters should be formed. So once we have the value of k, we specify that, and then the system will assign that many centroids. So it picks randomly to start with randomly that many points that are considered to be the centroids of these clusters. And then it measures the distance of each of the data points from these centroids and assigns those points to the corresponding centroid from which the distances are minimum. So each data point will be assigned to the centroid which is closest to it. And thereby we have k number of initial clusters. However, this is not the final clusters. The next step it does is for the new groups, for the clusters that have been formed, it calculates the main position, thereby calculates the new centroid position. The position of the centroid moves compared to the randomly allocated one. So it's an iterative process. Once again, the distance of each point is measured from this new centroid point. And if required, the data points are relocated to the new centroids. And the mean position, or the new centroid, is calculated once again. If the centroid moves, then the iteration continues, which means the convergence has not happened. The clustering is not converged. So as long as there is a movement of the centroid, this iteration keeps happening. But once the centroid stops moving, which means that the cluster has converged, or the clustering process has converged, that will be the end result. So now we have the final position of the centroid, and the data points are allocated accordingly to the closest centroid. I know it's a little difficult to understand from this simple flowchart. So let's do a little bit of visualization and see if we can explain it better. Let's take the example of if we have a data set for a grocery shop. So let's say we have a data set for a grocery shop, and now we want to find out how many clusters this has to be spread across. So how do we find the optimum number of clusters? There's a technique called the elbow method. So when these clusters are formed, there's a parameter called written sum of squares. And the lower this value is, the better the cluster is. That means all these points are very close to each other. So we use this within sum of squares as a measure to find the optimum number of clusters that can be formed for a given data set. So we create clusters, or we let the system create clusters of a variety of numbers. So maybe above 10 clusters, and for each value of k, the within SS is the measure, and the value of k which has the least amount of within SS or WSS, that's taken as the optimum value of k. So this is the diagonal metric representation. So we have on the y-axis the written sum of squares, or WSS, and on the x-axis we have the number of clusters. So as you can imagine, if you have k is equal to 1, which means all the data points are in a single cluster, the within SS value will be very high because they're probably scattered all over. The moment you split it into 2, there will be a drastic fall in the within SS value. That's what is represented here. But then as the value of k increases, the rate of decrease will not be so high. So it will continue to decrease, but probably the rate of decrease will not be so high. So from here we get an idea for an example. The optimum value of k should be either 2 or 3, or at the most 4. But beyond that, increasing the number of clusters is not dramatically changing the value of WSS, because that pretty much gets stabilized. Okay, now that we've got the value of k, and let's assume that these are our delivery points, the next step is basically to assign 2 centroids randomly. So let's say C1 and C2 are the centroids assigned randomly. Now the distance of each location from the centroid is measured, and each point is assigned to the centroid, which is the closest to it. So for example, these points are very obvious that these are closest to C1, whereas this point is far away from C2. So these points will be assigned, which are closest to C1 will be assigned to C1, and these points or locations which are close to C2 will be assigned to C2. And then this is how the initial grouping is done. This is the part of C1, and this is part of C2. The next step is to calculate the actual centroid of this data, because remember, C1 and C2 are not the centroids. They're randomly assigned points, and the only thing that has been done was that the data points which are closest to them have been assigned. But now, in this step, the actual centroid will be calculated, which may be for each of these data sets somewhere in the middle. So that's like the mean point that will be calculated, and the centroid will be actually positioned or repositioned. The same with C2. The new centroid for this group is C2, this new position, and C1 is in this new position. Once again, the distance of each of the data points is calculated from these centroids. Now remember, it's not necessary that the distance still remains, or each of these data points still remain in the same group. By recalculating the distance, it may be possible that some points get reallocated. Like, so if you see this one, this point earlier was closer to C2 because C2 was here. But after it was recalculated and repositioned, you can see that it is closer to C1 than C2. So this is the new grouping. So some points will be reassigned, and again, the centroid will be calculated. And if the centroid doesn't change during the iterative process, if the centroid doesn't change, once it stops changing, that means the algorithm has converged, and this is our final cluster, with this as the centroid C1 and C2 as the centroids, these data points as a part of each cluster. So I hope this helps you understand the whole process, the iterative process of k-means clustering. So let's take a look at the k-means clustering algorithm. Let's say we have x1, x2, x3, n number of points as our inputs, and we want to split these into k clusters, or if we want to create k clusters. So the first step was to randomly pick k points and call them centroids. Now they're not real centroids because the centroid is supposed to be the center point, but they are just called centroids. And we calculate the distance of each and every input point from each of the centroids. So the distance of x1 from C1, from C2, C3, each of the distances we calculate, and then we find out which distance is the lowest and assigned x1 to that particular random centroid. Then repeat that process for x2, calculate its distance from each of the centroids, C1, C2, C3 to CK, and find which is the lowest distance and assign x2 to that particular centroid. Same with x3 and so on. So that is the first round of assignments, if you will. Now we have k groups because we have assigned the value of k. So there's k centroids and there are k groups, and all these have been split into k groups. Now remember, we picked centroids randomly, so they're not real centroids. So now what we have to do is we have to calculate the actual centroids for each of these groups, which is like the main position, which means that the position of the randomly selected centroids will now change, and they will be the main positions of this newly formed K group. And once again, what is done is we go through the process of calculating the distance. So this is what we're doing as a part of step 4. We repeat step 2 and 3. So again, we calculate the distance from x1 from the centroid C1, C2, C3. And then we see which is the lowest value and assign x1 to that. Calculate the distance of x2 from C1, C2, C3, or whatever, all the way up to k, ck. And find whichever is the lowest distance and assign x2 to that, etc. So in this process, there may be some reassignment. x1 probably was assigned to cluster C2, and after doing the calculation, maybe now x1 is assigned to C1. So that kind of reallocation may happen. So we repeat the steps 2 and 3 until the position of the centroids does not change, or they stop changing. And that's when we have convergence. So let's take a detailed look at it, at each of these steps. So we'll randomly pick k cluster centers, and we'll call them centroids because they're not really the centroids. So we'll just name them C1, C2, all the way up to CK. And then step 2, we'll assign each data point to the closest center. So what we can do is we can calculate the distance of each x value from each c value. So the distance between x1, c1, the distance between x1, c2, x1, c3, and then we find which is the lowest value, or the minimum value we find, and assign x1 to that particular centroid. Then we go next to x2 and find the distance of x2 from c1, x2 from c2, x2 from c3, and so on up to ck, and then assign it to the point or the centroid which has the lowest value, and so on. So that's step number 2. In step number 3, we now find the actual centroid for each group. So what has happened as a part of step 2, we now have all the points, all the data points grouped into k groups because we wanted to create k clusters, right? So we have k groups, and each one may be having a certain number of input values, and they need not be equally distributed, by the way. Based on the distance, we will have k groups. But remember, the initial values of the C1, C2 were not really the centroids of these groups. We had just randomly assigned those. Now in step 3, we actually calculate the centroid of each group, which means the original point, which we thought was the centroid, will shift to the new position, which is the actual centroid for each of these groups. Okay, and we again calculate the distance. So we'll go back to step 2 and then calculate the distance of each of these points from the newly positioned centroids. And if required, we reassign these points to the new centroids. So as I said earlier, there may be a reallocation. So now we have a new set or a new group. We still have K groups, but the number of items and the actual assignment may be different from what it was in step 2 here. Okay, so that might change. Then we'll perform step 3 once again to find the new centroid of this new group. So we have, again, a new set of clusters, new centroids, and new assignments. We repeat this step 2 once again. And once again, we find that it is possible that after running through 4 or 5 iterations, the centroid will stop moving, in the sense that when you calculate the new value of the centroid, it'll be the same as the original value, or there'll be very little or marginal change. So that is when we say convergence has occurred, and that is our final cluster. So that's the formation of the final cluster. All right, let's take a look at a couple demos of k-means clustering, some actual live demos. First, we have to determine what is the problem that we're trying to solve. So let's say Walmart wants to open a chain of stores across the state of Florida, and it wants to find the optimal store locations. Now, the issue here is if they open too many stores close to each other, obviously they will not make profit, but if the stores are too far apart, then they don't have enough sales. So how do they optimize the locations? Now, an organization like Walmart, which is an e-commerce joint, they already have the addresses of their customers in their database, so they can actually use this information or this data and use k-means clustering to find the optimal location. Now, before we go into the Python notebook and show you the live code, I want to take you through very quickly a summary of the code in the slides, and then we will go into the Python notebook. So in this block, we are basically importing all the required libraries like NumPy, Matplotlib, and so on. And we are loading the data that is available in the form of, let's say, the addresses. For simplicity's sake, we will just take them as some data points. And then the next thing we do is we'll quickly do a scatter plot to see how they are related to each other with respect to each other. So in the scatter plot, we see that there are a few distinct groups already being formed. You can actually get an idea about how the cluster would look and how many clusters, or what would be the optimal number of clusters. And then starts the actual k-means clustering process. So we will assign each of these points to the centroids, and then check whether they're the optimal distance, which is the shortest distance, and assign each of the points, the data points, to the centroids. Then go through this iterative process until the whole process converges. And finally, we get an output like this. So we have 4 distinct clusters, which is, if we can say that this is how the population is probably distributed across Florida state. And these centroids are like the location where the store should be, the optimum location where the store should be. So that's the way we determine the best locations for the stores. And that's how we can help Wawa find the best locations for stores in Florida. So now let's dump this into Python notebook and see how it looks when we're running the code live. All right, so this is the code for k-means clustering in Jupyter Notebook. We have a few examples here which we will demonstrate how k-means clustering is used, and even there's a small implementation of k-means clustering as well. So let's get started. So this block is basically importing the various libraries that are required like matplotlib, numpy, and so on and so forth, which would be used as part of the code. And then we are going to be creating blobs, which are similar to clusters. Now this is a very neat feature which is available in Scikit-learn. Make blobs is a nice feature which creates clusters of data sets. So it has wonderful functionality. It's readily available for us to create some test data kind of things. So that's exactly what we're going to do here. And we're using make blobs. We can specify how many clusters we want. So we see we're mentioning centers here, and we're just going to mention 4 centers. So it'll go ahead and create some test data for us. And this is how it looks, as you can see visually. Also, we can figure out that there are 4 distinct classes or clusters in this data set. And that is what make blobs provides. Now, from here onwards, we will basically run the standard k-means functionality that is readily available. So we really don't have to implement k-means itself. The k-means functionality or the function is readily available. You just need to feed the data and create the clusters. So this is the code for that. We import k-means, and then we create an instance of k-means, and we specify the value of k. So remember that k in k-means clusters is the value of the number of clusters that you want to create, and it's an integer value. So this is where we are specifying that. So we have k is equal to 4. So that instance is created, and we take that instance as with any other machine learning functionality. Fit is what we use, or the function or the method rather. Fit is what we use to train the model. Here there's no real training of any kind, but that's the call. So we are calling fit, and what we are doing here is we're just passing the data. So x has these values, the data has been created. So that is what we're passing here. And then this will go ahead and create clusters. And then we are using, after doing fit, we run the predict, which basically assigns for each of these observations which cluster it belongs to, right? So it will name the clusters, and maybe this is cluster 1, 2, 3, and so on, or actually it might start from 0, cluster 0, 1, 2, and 3 maybe. And then for each of the observations, it will assign, based on which cluster it belongs to, it will assign a value. So that is stored in y underscore k-means. When we call predict, that's what it does. Now, we can take a look at these cluster numbers that have been assigned for each observation. So this is the cluster number assigned for observation 1 maybe. This is for observation 2, 3, and so on. So it looks like we have about 300 samples, right? So all 300 samples, there are 300 values here, and each of them cluster number is given. And the cluster number goes from 0 to 3, so there are 4 clusters. So the numbers go from 0 to 1, 2, and 3. So this was just a quick example of generating some dummy data and then clustering that. And this can be applied if you have proper data. You can just load it up into X, for example, here, and then run it. Okay, so this was a central part of the k-means clustering program example. So you basically create an instance, and you mentioned how many clusters you want by specifying this parameter and underscore clusters, and then there's also the value of k. And then pass the data and get the values. Now in the next section of this code, the implementation of k-means, this is kind of a rough implementation of the k-means algorithm. So we'll just take a walk through, and I'll walk you through the code at each step and tell you what it's doing, and then we'll see a couple of more examples of how k-means clustering can be used in some real-life situations, real-life use cases. In this case here, what we're doing is basically implementing k-means clustering, and there is a function where the library calculates for a given 2 pairs of points. It will calculate the distance between them and see which one is the closest, and so on. So this is pretty much what k-means does, and so it calculates the distance of each point or each data set from a predefined centroid, and then based on whichever is the lowest, that particular data point is assigned to that centroid. So that's basically available as a standard function, and we will be using that here. So as we explained earlier, the first step that is done in the case of k-means clustering is to randomly assign some centroids. So as a first step, we randomly allocate a couple of centroids, which we see here we're calling them centers, and then we put this in a loop, and then we take it through an iterative process. For each of the data points, we first find out using this function pairwise distances argmin. For each of the points, we find out which center or which randomly selected centroid is the closest. And accordingly, we assign that data or the data point to that particular centroid or cluster. And once that is done for all the data points, we calculate the new centroid by finding out the mean position, which is the center position. So we calculate the new centroid, and then we check to see if the new centroid, the coordinates or the position is the same as the previous centroid. The positions we will compare, and then if it is the same, that means the process has converged. So remember, we do this process until the centroids or that centroid doesn't move anymore. So the centroid gets reallocated each time. And once the movement doesn't change anymore, or that position of the centroid doesn't change anymore, we know that convergence has occurred. Until then, you see here, this is like an infinite loop. While true is an infinite loop, and it only breaks when the centers are the same. The new center and the old center positions are the same. And once that is done, you can see we return centers and labels. So this is not a very sophisticated implementation. It's very basic. Because one of the flaws in this is that sometimes what happens is the centroid position will keep moving, but the change will be very minor. So in that case, we could consider that convergence. For example, say the change is 0.0001. We can consider that to be convergence. Otherwise, what will happen is this will either take forever or it will be never ending. So that's a small flaw here. For that reason, additional checks may have to be added. But again, this example is a very simple implementation of k-means clustering. Okay, so if we execute this code, this is what we get as the output. So this is the definition of this particular function. And we call that find underscore clusters. And we pass our data x, number of clusters, which is 4. And if we run that and plot it, this is the output that we get. So we see here that each cluster is represented by a different color. We have a green cluster, yellow cluster, and so on and so forth. And these big points here, these are the centroids. This is the final position of the centroids. And you can see visually also that this appears kind of to be a center of these points right here. And similarly, this is like the center of all these points and so on. So this is an example of an implementation of k-means clustering. So next, we will move on to see a couple of examples of how k-means clustering is used in maybe some real-life scenarios or use case examples. In the next example or demo, we're going to see how we can use k-means clustering to perform color compression. We'll take a couple of images, so there will be 2 examples, and we will try to use k-means clustering to compress the colors. This is a common situation in image processing when you have an image with millions of colors, but then you cannot render it on some devices which may not have enough memory. So that is a scenario where something like this could be used. So again, before we begin, we go into the Python notebook. Let's take a look quickly at the code. As usual, we import the libraries, and then we import the image, and then we will flatten it. So the reshaping is basically, we have the image formation is stored in the form of pixels. And if the image is, like for example, 427 by 640, and it has 3 colors, So that's the overall dimension of the initial image. We just reshape it and then feed this to our algorithm. And this will then create clusters of only 16 clusters. So these are the colors that are the millions of colors. And now we need to bring it down to 16 colors. So we use k is equal to 16. And when we visualize it, this is how it looks. There are about 16 million possible colors, or the input space has 16 million possible colors. And then we just subcompress it to 16 colors. So this is how it would look when we compress it to 16 colors. So this is how the original image looks, and after compression to 16 colors, this is a look at the new image. And you can see there's not a lot of information that has been lost, though the image quality is definitely reduced. So this would be an example of which we're going to now see in Python. So let's go into Python, and once again, as always, we will import some libraries and load the image called flower.jpg. So let me load that, and this is how it looks. This is the original image, which I think has 16 million colors. And this is the shape of the image, which basically it's the pixels, the 427 by 640 pixels. And then we see 3 layers, which is basically for RGB, which is red, green, and blue. So that is basically the shape of this. So what we need to do now is take a look at how the data looks. So let me just create a new cell and show you what is in the data. Basically, we have captured this information. So the data is, let me just show you here. All right, so let's take a look at China. What are the values in China? And if we see here, this is how the data is stored. This is the pixel values, okay? So this is like a matrix for each one, which has about 427 by 640 pixels, right? So this is how it looks. And the issue here is these values are large. There are a lot of numbers, so we need to normalize them to between 0 and 1. So that's why we'll basically create one more variable, which is data, which will contain the values between 0 and 1. And the way to do that is to divide by 255. So we divide China by 255, and we get new values in data. So let's just run this piece of code. And this is the shapes that we have now. Also, what we have done is changed using reshape. We've converted these into 3-dimensional or 2-dimensional data sets. And now let's take a look to, let me just insert probably a cell here and take a look at how the data is looking. So this is how the data is looking. And now you see these are the values between 0 and 1. So if earlier you noticed in the case of China the values were large numbers, now everything is between 0 and 1. And this is one of the things we need to do. So after that, the next thing we need to do is to visualize this. And we can take a random set of maybe 10,000 points and plot it and check to see how this looks. So let's just plot this. So this is how the original color with the pixel distribution is. And there are 2 plots. One is red against green and the other is red against blue. And this is the original distribution of the color. So then what we'll do is we'll use k-means clustering to create just 16 clusters for the various colors, and then apply that to the image. Now what will happen is, since the data is large, because there are millions of colors, using regular k-means may be a little time consuming. So there's another version of k-means, which is called mini batch. So we will use that, which processes the overall concept remains the same, but basically it processes it in smaller batches. That's the only difference. So the results will be pretty much the same. So let's go ahead and execute this piece of code, and then we can visualize this. So we could see this is how the 16 colors would look. So this is red against green, and this is red against blue. So there is quite a bit of similarity between the two color schemes. and we could see that the new one doesn't look too different or anything like that. Now we apply this to the newly created colors to the image, and we can take a look at how this image, or now we can compare both images. So this is how our original image looked, and this is our new image. So you can see there's not a lot of information that has been lost. Pretty much looks like the original image. Though we can see, for example, here we've appeared to lose a little bit of detail compared to this one, because we kind of took out some of the finer details of the color. But overall, the high-level information has been maintained. At the same time, the main advantage is that now this can be an image which can be rendered on a device which may not be that very sophisticated. Now let's take one more example with a different image. In the second example, we will take an image of a palace in China, and we repeat the same process. This is a high-definition color image with millions of colors, and also three-dimensional. Now we will reduce that to 16 colors using k-means clustering, and we use the same process we did before. We reshape it, and then we cluster the colors to 16, and then we render the image once again, and we will see that the color, the quality of the image slightly deteriorates, as you can see here. This has much finer details in which are probably missing here, but then that's the compromise, because there are some devices which may not be able to handle this kind of high density images. So let's run this code in Python Notebook. All right, so let's apply the same technique for another picture, which is even more intricate, probably has a much more complicated color schema. So this is the image. And once again, we can take a look at the shape, which is 427 by 640 by 3. And this is the new data, would look something like this compared to the flower image. So we have some new values here, and we will also, as you can see here, the numbers are much bigger. So we'll now have to scale them down to values between 0 and 1. And that's done by dividing by 255 again. So let's go ahead and do that. I'd reshape it. So we get a two-dimensional matrix. And then as the next step, we will go ahead and visualize this in 16 colors. And this is basically how it look. 16 million colors. And now we can create the clusters out of this. The 16K means clusters. We will create, so this is how the distribution of the pixels would look with 16 colors. And then we go ahead and apply this and visualize what it looks like for the new, just with 16 colors. So once again, you can see this looks much richer in color, but at the same time, this probably doesn't have it doesn't look as rich as this one, but nevertheless, this information is not lost on the shape and all that stuff. And so this could also be rendered now on a device which is not as sophisticated. So that's pretty much it. We've seen two examples of how color compression can be done using k-means clustering. And we have also seen in previous examples how to implement k-means, the code, roughly how to implement k-means clustering. And we've used some data using blob to just execute the k-means clustering. All right, so let's move on. So let's summarize what we have learned in this video. We started with an example of how we can apply k-means clustering, taking the cricket example. And then we talked about the types of clustering, two major categories, hierarchical clustering and partition clustering, which in turn had two subcategories, agglomerative and divisive, and then k-means and fuzzy C. And then we discussed the distance measures, the different types of distance measures supported by k-means clustering. And we focused on k-means clustering. We talked about its applications and how the process flow works for k-means clustering. And then finally, we ended up with a demo and a couple of use cases. All right, so with that, we've come to the end of this video. Thank you very much for watching. And with that, if you have any more questions, please feel free to visit us at www.simplylearn.com. You may also add your comments and feedback at the bottom of this video. Thanks once again. I'm Douglas for Simplilearn.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.